Alright, hello world. Last time we had started a section on Majorant series. You're given two power series, essentially. Let's call them A and P. There were some other conditions here, like the A's are complex and the P's are, the P coefficients are real. But in any case, if the magnitude of the A's are always less than the P values, then use this notation and you call P a majorant of A, or A minorant of P. And so last time we did just the first two, 61 and 62. 61 was pretty obvious. It's really just write down the definition. It falls out immediately. 62, if you know, I did it using Taylor's theorem, like Taylor series expansion for e to the z. And then it was pretty obvious. There doesn't seem to be anything wrong with that. He didn't do it that way, though. He seems to have used 61 to get it. His answer for 62, I didn't really look too closely at it. I mean, it's probably a good result in general to know this. But I don't think this this wasn't really necessary. You could also do it with Taylor's theorem. Like I did a binomial. Yeah, the only step that was a little, required maybe half a second of thought was I used the binomial theorem on the left-hand side, but that doesn't fall apart or anything as long as n is not a fraction. So for for an integer like this, you just use binomial theorem and compare it to the Taylor series expansion. Think about that again real quick. Yeah, my thought process had been, if we have this, right? So it's something like this. Right? But, so all I need to do is show that some of the time these terms are 0, while e to the z, like this is less than e to the z. E to the z is, there's your z to the k, but you also have these terms. These terms. So if you multiply by this, you get n times, like right here you get n minus 1, n minus 2, k times. But then downstairs we have n times itself, k times, because it's n to the k. And that's less than 1. So this coefficient is definitely less than 1 over k factorial. So yeah, I don't see what the issue was with just using a straight Taylor's theorem expansion, but maybe it's worth thinking about what he wrote here. If you have positive a's, then a sub v, oh I see, I was misreading, I was confused what this notation was, I get it now. 1 plus any coefficient times z would be majorized by e to that coefficient times z. So that's his first statement. And then by 61, the one we just saw, we can take like a product of these, and it'll be majorized by, we just basically repeat this. Guess I don't really directly see how that's 61, right? I thought these were supposed to be conjugates. Is there a notation thing? I think he used it a long time ago, so he's not going to mention it again. Yeah, it's got to be conjugate, right? Well, I don't know. It never showed up, I guess. So yeah, I'm supposed to just know that it's the conjugate. Yeah, I don't think it ever showed up. Huh. Right. No, it didn't. Oh yeah, it's not going to be a notation back here. All right, sir. Well, so this is like saying 1 plus a value is less than e to that value. They agree at 0, but then, so like if you drew this, you could also draw a line that touches here, but if you look at the derivatives, the derivative of this is 1, the derivative of this is greater than 1 as soon as you plug in x values that are positive. So this is certainly true, just immediately from some basic calc. So this is always true. I'm not sure why he used this notation for it. But then he basically took a product, which is where I'm like, I'm not sure what that has to do with 61. Anyway, you can just let the a1s be 1 over n, and you'll get exactly what we were talking about. And on the right, you get n to the I guess you get e to the z on the right-hand side, right? You have n sums of 1 over n. So it clearly follows from that case. I guess I'm feeling kind of dumb about this. I still don't know what this has to do with 61. Because I interpreted this as a conjugate. I mean, I'm sure it's true. It's like the same spirit as 61. Yeah, okay. Maybe that's all he's saying, is in the same manner that you proved 61. Follows from the definition. For the product, yeah, use 34. Yeah, we don't need to prove it again. It's pretty clear. Alright, that's fine. So that's 62. You could do it a different way. I did it, I guess maybe I should have done it his way. His way is simpler if you think about it. It's a little more fundamental to what we're doing. It doesn't even involve an expansion of E, right? Even if you didn't have that, you would get this result. So all right. I guess it's a little confusing to me to keep using this notation when you have a finite sum. Like, this is a polynomial, and this is not. You know, it's like the a in this case only has a finite number of terms. But anyway, let us move on. I haven't looked at these yet. 63 says you got basically a power series. Suppose that this happens for your function. Deduce that all the coefficients are less than n. I'm not sure how I'm going to get there. But yeah, we're looking at 63 now. And it says, oops. It says, suppose you have a function it's z plus a2z squared plus a3z cubed, yada yada. If you're given that z f prime over f of z is bounded by, is majorized by 1 plus z over 1 minus z, then you'll also be able to show that the magnitude of these coefficients is always bounded by n. So that's our goal at the moment. I'm not sure how I'm getting there, but when you do take a derivative, you're getting 1 plus 2a2z plus 3a3z square, etc. So in general you get like k, ak, z to the k minus 1. But then I multiply it by z, so it bumps it back up. So z f prime z over fz looks something like z plus, and then you have the original thing, you just have an extra number. So it's z plus 2a2 z squared. Downstairs you just don't have those extra coefficients like the number 2. The only other thing I'm noticing, the only other thing that occurs to me is we could maybe rewrite this, right? This is like 1 plus 2z over one minus z. Right, you can write this as 1 minus z plus 2z. So, I don't think that helps us, but... Okay, well, so it's obviously true if you only have like the single term, right? You end up with something like 1 is less than 1 plus this function. And I was kind of acting like this is never negative. But maybe it is a problem. Yeah, it doesn't mention... I imagine this is the whole complex plane, I guess. Oh, it's in magnitude. It's okay if it's negative. Huh, weird. Well, on the left you'd be getting a 1 in that case, right? If all the a's were 0, I'm saying, you just get 1 on the left. So this condition tells us, okay, this condition actually tells us that 1 is majorized by this. Huh. Anyway, it's kind of a stupid example, right? Because this is like immediately true in that case. Yeah, I'm not sure how to get a grip on this left-hand side. It's a bit like... I mean, I see it's a bit like z times the derivative of log, but I don't think that's where we're supposed to go with it. Like if you looked at this function first. Well, not even this function, right? It'd be this, yeah, z times the derivative of log is what I'm saying. I don't know, I don't love it. I don't know what he says here. So 63. He gives us sort of a new inequality. I mean, yeah, that's obvious, right? Sure. Oh, is this another way of phrasing the, yeah, maybe we should rewrite that. He mentions that we have this, what is it, 2 over 1 minus z. So we should probably deduce that first from what we've been given. Huh. Did he just divide? Why would this be a 2 though instead of a 1? Huh. No. Oh, because of this. Okay, so he did do this. I see. And then is that majorized? Yeah, it is. Okay. So he first points out that we have this as well. If you just the right-hand side, you express as this, right? So it's a 1. You subtract the 1, and you get this after you divide by z. It'll get rid of this too. So we do have this. All right. So moving on. So did it involve a log of f over z? It's not quite what I thought of. Alright, so we have this. Looks like he took a logarithm of it and This part's fine. Oh, okay. So he did do this log trick with f. Although he doesn't mention it, so maybe he didn't. So, of course, the inequality implies that you can integrate or you can apply an increasing function to both sides. You still have the same inequality. This was the condition we were given. And he's saying this leads to this, and this leads to that. Like here, since this is true, you can just exponentiate both sides, and you get this statement. And so f is majorized by, well, the coefficients of f are bounded by n. You can see right now, if you multiply by z, we're done as soon as you wrote this down. So yeah, my only concern is getting there. It's obviously just took a log of both sides, but I'm feeling kind of dumb about this part. He integrate also, and I'm just not. Yeah, he must have integrated this. Well, no, because the z is there, right? He didn't integrate that. And yeah, you can't do that. He must have, you can't just take a log of this and combine it like that. So he clearly integrated first. Like, So yeah, if we had two integrals of 1 over 1 minus x dx, what is that? It should be, is it negative 2 log? Yeah, why wouldn't it be this? And if you take the antiderivative on the left, you appear to get log f minus log z. Ah, that's what he did. So, good. So that's where you get this comes from. But on the right, oh, it's negative. Good. That makes sense. Okay, on the right, you're getting this. That's what he wrote. Okay, good. Okay, so he did need each of those comments. Like he mentions that you're able to integrate. Wow, all right. I'm glad I didn't spend any more time trying to do this one. I was trying to do it like directly with coefficients. And I noticed the log f thing. Like I noticed it's the derivative of log f, but that didn't really help me get anywhere. All right. That's not bad. 64. Suppose you have these integers. Prove the following relations either with or without number 9's results. So number 9, I should probably remember by this point. Number 9 is this, basically generalizing all the results that we did in the first 8 problems. So back then we were counting, it's a bunch of combinatorics cases. So for instance, the A series comes from the number of solutions. Like, if you let A(n) denote the number of solutions to this kind of equation, so the first problem was like, how many ways can you make change using, say, a penny, a nickel, a dime, a quarter, and a $50? So that's where this equation comes from, is a sort of combinatorial question. But then we have this generating function. So the coefficients represent the number of solutions to those. Although I don't recall a nice. Yeah, we must have counted it some way. What was that? Like if you were trying to solve what I just looked at, x plus 5y plus 10z. Suppose we're just solving that. With positive, well, non-negative x, y, z. What you can do is jot down all the powers that would result from terms like this first one. So x could be 0 or 1 or 2 or 3, etc. And then jot down all the powers that result from multiples of this second coefficient. So that could be y is 0, or y is 1, or y is 2, etc. And then this last guy, z is 0, or z is 1, or z is 2, etc. And when you multiply these together, every time that you have a particular power, zeta to the n, its coefficient is the number of ways that you could have constructed that sum. So this is the kind of function, and it's the product of these. So this is a generating function for that type of problem. So then we've translated the number of solutions to this to be a question of like, all right, what are the coefficients of this product? If you can find the nth coefficient of this product of these three factors, then you would have solved, the number of solutions of this equation. So that's what he means by A, the sequence AN. Back in number 9, he generalized these types of problems. Like, after you had solved a bunch of them, the first 8 problems. So that was number 2 or number 1. Then BN is more like permutations. A simpler example back then was, how many ways can you arrange stamps? We have 2, 4, 6, 8, and we need the postage to be 10 cents total. So one that's not different is if you had like 5 stamps too, like 2, 2, 2, 2, So it's a similar question to like partitions of a number. Or you could have like 2, 4, 4, or you could have 2, 2, 2, 4, right? Or 4, 2, 2, 2. Those are different. So what are the number of possible sums whose terms are blah? 2 sums. Different arrangements of the same value are regarded as different, right? 2 sums consisting of the same terms in a different order are regarded as different. So this time, this B coefficients, that's why I said permutations. It's not just the number of solutions, but it's all arrangements of those solutions. So let me think about how we did that one. Did he give me an equation for that one? I can't quite remember. No, not really. It's the number of sums with terms whatever, like 1, 2, 3, 4. So another question is number of sums where the order matters with terms say 1, 2, 3, 4. And the way you'd approach that is to write out zeta, zeta squared, zeta cubed, zeta 4, right? Notice I did not include 0, so there's no 1 here because we're not going to add 0 to our sum. So the only powers that I would put here would be the powers that you're allowed to include in your sum. And then if this is only one term, like that term could be 1 or 2 or 3 or 4. And now what you do is if you want like k terms, you just put a power k here. All right. And then if you were trying to solve for like how many ways can we arrange these numbers as summands, as terms in a sum in such a way to get a sum of n, then you're looking for the nth coefficient in this expansion. I suppose we could let this just be an infinite product if you want, because eventually for any finite n, it's gonna stop having contributions at some point, and after n terms, right? But anyway, the coefficients of such an expansion are what we called Bn back in number 9. And then the last case is with weights. He says, number 5 maybe? Yeah, 5 was the first simpler example, and then he included negative numbers. But basically, the third series that he discusses, the third generating function, is solving stuff like this, where the e's can be, I guess if you're going for C, the e's can be positive. They're either 0 or they're 1. And then the more general case is that you're able to subtract numbers as well. And in that case, he called it series D, and he allowed the e's in this equation to take on value -1 as well. The base case of this, the simple example that he gave us, was something like you have, suppose you have 8 weights. Some of them double up, so we've got 2 1s, we've got 2 10s. You have 8 weights, like a 1, 1, 2, 5, etc., grams. How many ways can you measure 78 grams? So how many ways can you construct 78 grams out of these? And he picked the numbers nicely enough that you can just go, 50 and 20 is 70, and we make an 8 somehow, right? There's 2 different ways to make 8, because we've got 2 1s. So with these particular numbers, there's 2 different ways to make 8. And then there's also 3 different ways to make 20. Two different ways to make 20. So 50 plus 20 or 50 plus 10, 10 will get you to say, anyway. So you can kind of quickly count in this simple case. But more generally, you're solving, you're finding the number of ways that we can solve this equation using a 0 or a 1 for the e's. You set this equation equal to 78, and you say, all right, how many ways can I solve that? That's a more organized approach. But what we can do is come up with, his question back then on number 7 was like, suppose you have a generating function where the coefficients Cn represent the number of solutions to this being equal to n. What is that polynomial? Like, write it as a product. And so again, it sort of involves what is this one? Oh, well, we're only allowing 0 or 1 as possible values, so it's got to be something like 1 plus zeta, right? Here's one possible solution. Yeah, this is what it's going to be. So you just write out things like that. This would be 0 or 1. And this, in our case, the example you just saw, we had like 2 1-gram weights, so that's why I have a second copy of this. But then maybe we have like a 2-gram weight, and that's this contribution. You'll put a 2 there. Maybe we have like a 5-gram weight, and you'll put a 5 here, etc. Maybe I'll stop. We'll write one more. Like 8. I don't think that was one of them, but I'm just Maybe it was. I can't remember. Yeah, probably it was. Like 8 and 2 make 10. So I don't know. Anyway, this would be you finding this product would represent a generating function for you trying to solve an equation like, let's not do x. Let's do e1 plus e2 plus 2e3 plus 5e4 plus 8e5. All right, so now if I set this equal to n, how many solutions are there where the EIs can be either 0 or 1? That's analogous to our question about the weights. But yeah, the number of solutions to this equation under this condition is given by the nth coefficient of this expansion if you were to multiply this product out. Those coefficients are going to be called Cn. So that's the background. Why am I talking about all this? Because question 64 referred to number 9. So we needed to know this stuff as background if you want to have a smooth time answering this question. The first one looks like the one I just brought up, right? There's two terms, and you got a product of a bunch of things with just two terms. So that's, the first case is the CNs. The second case looks like, I guess like this one, right? 1 over 1 minus z to some power, where the power is like the weight that you're using. So this product is the generating function for A. And then the last one, yep, is 1 over 1 minus a big sum, a lot like this. If you took the sum as k goes from 0 to infinity, you'd be looking at a geometric series with this as the base. In other words, if we sum this as k goes from 0 to infinity, you get 1 over 1 minus, and then you put that as the base. Right? So his question was, demonstrate that, for positive integers anyway, this relation is true. If you have the product of 1 plus z to those powers, it's less than 1 over 1 minus z to those powers, which is less than 1 over 1 minus this chunk. So it never occurred to me before, but I guess it's the case that Cn is less than An, which is less than Bn. And that's the end of 64. If that were obvious, then we would be done with 64. So we could have made these the same numbers. That maybe would have made our life a little easier. So if you imagine if you imagine this was zeta to the 1, zeta to the 5, zeta to the 10. In this first case, we allowed them to be any non-negative number. But in this case, we only allow the coefficients to be 0 or 1. So of course there are fewer, you immediately get the first part. It's obvious. If instead of this equation, you looked at So instead of this equation with any, well, here, I'll just write them down. If instead we had E1 plus 5E2 plus 10E3 equal to n, where you only allow the EIs to be 0 or 1, I'm saying this definitely has fewer solutions in general than this guy. And so it's obvious that Cn is less than An. How do we compare An to Bn? Bn is going to have more because, first of all, they're permutations. Like, you're telling me that the order suddenly matters, which it didn't before. So that's another reason this is obvious, the second inequality. I mean, that's the reason that I have for why it's obvious. Let's see. I didn't write down an equation purposely on the Bn case but it would be similar to solving. So we again solve this equation, but this time we say solutions are different if you arrange the entries, the terms, differently. So you have all the same solutions that you had in the A case, but now you have many more. I mean, you have it's at most whatever the number of terms is. Say there were k terms. It's potentially k factorial more. It's actually less because some of them double up, right? So if you had 5, 1, 5, you don't actually get 3 factorial, right? You get 3 factorial over 2 factorial arrangements because these two are the same. So you have to divide by the number of ways that you overcounted by swapping the 5s. But for instance, in that case, there's 3 different arrangements, whereas in the A case, the original case, there was only 1. The arrangements don't matter in that case. So that's why this second inequality is true. And that's the end of 64 in the easy way to show it. So prove this result twice. First of all, if you do apply 9, it's what I just described here. Without applying 9, let's see, if we I could sort of see, what if we, here, let's think about it. So we're doing 64 again. I'm trying to show that if you took something like 1 plus z to the a times 1 plus z to the b, that's less than 1 over 1 minus z to the a, 1 minus z to the b, right? If I just multiply by this, don't I immediately get something like this? So, okay, I do maybe have a problem. I thought it was a bunch of negatives. I was thinking that this is clearly positive, so that I thought we were done here, but the problem is you've also got this term. So is it always the case that z squared to the ab is going to be less than z squared a plus z squared b? That feels obvious, but I'm a little... X to the AB always less than x to the A plus x to the B. Is this an obvious geometric? Is this just like the triangle inequality and I can't think straight right now? And then the other inequality was that this is less than 1 over 1 minus ZA minus ZB, like that. So another way to phrase this is like, we do get the... Yeah, no, you're fine. We do get downstairs, we get ZA minus ZB, but then we have an extra term, right? ZAB. And I was just trying to show that this is less than 1. Which seems kind of obvious. But maybe I'm ignoring some cases. Yeah, I mean, in magnitude, I don't really see anything wrong with that. So, yeah, let's see what he had to say. First part state follows immediately from this. Oh, of course, sure. Sure. So you could expand this as a geometric series, and the first two terms are right there. And notice he is ignoring like negative z's, just like I was. I presume because we're talking about majorants here, so we're talking about the magnitude of the numbers. Not just straight inequalities. All right, blah, and then where we put and multiply by 61, and multiply. Oh, I see. He's referring to 61. Yeah. Sure. Second part follows from I think I'm gonna have to call it there for today, guys. But just trying to make sure this makes sense. This minus that, which for one part is 1, but then you get a bunch of positive terms. Sure, yeah, right. And he's saying in magnitude that's clearly bigger than 1, sure. And then Ah, okay. Yeah, I think I'm going to leave that there for today. So we did 63, 64. You have yourself a great day.